Hello everyone, myself Riya Jain. My roll number is IT2K2049 and this video is a part of my assignment given to us by Dr. Shaligram Prajapat sir. And in this video, I am going to provide the solution of end semester exam paper. And here is the first question. Analyze the time complexity of the quicksort algorithm in average case and provide a step-by-step explanation of the sorting process. The average case time complexity of the quicksort algorithm is order of n log n, where n represents the number of elements to be sorted. And here is the step-by-step explanation of the quicksort algorithm. Choose a pivot element from the array. This can be done in various ways, such as selecting the first element, last element, or a random element. Partition the array into two subarrays, that is, element smaller than the pivot and the element greater than the pivot. This step rearrange the array such that all the elements smaller than the pivot come before it and all the elements greater than the pivot come after it. The pivot element is now in its final sorted position. Recursively apply step 1 and 2 to the subarrays formed in the previous step. This means selecting a pivot for each subarray and partitioning them until the subarrays contain only one element or are empty. Combine the sorted subarrays to get the final sorted arrays. The time complexity of the quicksort algorithm in the average case is determined by the number of comparison and swaps performed during the partitioning step. On average, the partitioning step divides the array into two subarrays of roughly equal size. Therefore, in each recursive call, the algorithm works on approximately half the elements of the previous subarray. This results in a time complexity of order of n log n for average case, as the total number of elements processed at each level of recursion is n and the number of level is log n. Let's move to the second question. Critically evaluate Stressen's matrix multiplication algorithm and compare its time complexity with the traditional matrix multiplication method. Stressen's algorithm for matrix multiplication is a divide and conquer approach that improves the asymptotic time complexity compared to the traditional matrix multiplication method. However, it has some practical limitations. Stressen's algorithm has a time complexity of order of n to the power 2.81, where n is the dimension of the matrices. This complexity is better than the traditional matrix multiplication method, which has a time complexity of order of n cube. For large matrices, Stressen's algorithm can be faster than the traditional method. However, there are some practical considerations to be keep in mind. Stressen's algorithm require the matrices to be of size that is a power of 2. If the input matrices do not have dimension that are power of 2, padding is needed, which increases the memory usage. Additionally, Stressen's algorithm involves more arithmetic operations compared to the traditional method, which can lead to increased numerical errors. Moreover, the advantage of Stressen's algorithm over the traditional matrix for small matrices due to the algorithm recursive overhead. Let's move to the third question. Evaluate Prim's algorithm for finding the minimal spanning tree and provide a real world scenario where it can be applied. Prim's algorithm is a greedy algorithm used to find the minimum spanning tree of a weighted undirected graph. It starts with an arbitrary vertex and iteratively adds the closest vertex not yet included in the MST. Until all vertices are included, the algorithm guarantees that the resulting tree will be the MS tree. Evaluation of Prim's algorithm. Time complexity of Prim's algorithm is order of V square with a naive implementation using adjacency matrix, or order of V plus E log V with a more efficient implementation using a priority queue. Space complexity of this algorithm is order of V for storing the minimum spanning tree. Real world scenario. Prim's algorithm can be applied to the design efficient communication network. For example, in the construction of a telecommunication network, where cities are represented at a vertices and the cost of the connecting cities is represented as age weight. Prim's algorithm can be used to determine the optimal network layout, ensuring that all cities are connected with a minimum total cost. This helps in minimizing infrastructure costs and optimizing communication efficiency between cities. Next question is, analyze Hamiltonian cycle and provide an example of how they can be used in real life application. A Hamiltonian cycle is a path in a graph that visits every vertex exactly once and ends at the starting vertex. It is a cycle that traverses all the nodes of the graph. Hamiltonian cycle have various real life application, including the first is traveling salesman problem. The traveling salesman problem involves finding the shortest route that visits a set of cities exactly once and return to the starting city. Hamiltonian cycle can be used to solve traveling salesman problem by finding the optimal tool for a salesperson to minimize travel distance. The second is circuit board testing. In electronic circuit testing, Hamiltonian cycle can be utilized to design an efficient test pattern that covers all points on the circuit board while minimizing the distance traveled by the testing problem. DNA sequencing. In genetic research, Hamiltonian cycle can be employed to sequence DNA fragments by finding the optimal path through overlapping segments of DNA, allowing for the reconstruction of the complete DNA sequence. Next is robot path planning. Hamiltonian cycle can be applied in robotics for path planning where a robot needs to traverse all specific location without revisiting any location. The cycle helps in determining the most efficient order of visiting the location. Network routing. Hamiltonian cycle can be used in network routing algorithm to find efficient path for data packet to travel through a network, ensuring that all nodes are visited. These are just a few examples of how Hamiltonian cycle can be used in real life application. They provide a way to solve optimization problem and efficiently navigate through interconnected system. Next question. Apply analytical perspective to develop a greedy algorithm for sequencing unit time jobs with deadlines and profit. Discuss the advantages and limitation of this approach. Derive the time. A greedy algorithm for sequencing unit time job with deadlines and profits can be developed using the following steps. The first step is sort the job in decreasing order of their profit. Second step is initialize an empty sequence and an array to keep track of the time slots. Third step is for each job starting from the highest profit, find the earliest available time slots before its deadline. If a time slot is available, assign the job to that slot and update the array. If no time slot is available, skip the job. The fourth step is the resulting sequence will be the optimal sequence. Now, advantages of this greedy algorithm approach. Efficiency. The greedy algorithm has a time complexity of order of n square, where n is the number of jobs. This makes it efficient for small to moderate sized problem instances. Simplicity. The algorithm is relatively easy to understand and implement. Optimality. The greedy algorithm guarantees finding a feasible solution that maximizes the total profit when jobs have unit time. Now, we see the limitation of this greedy algorithm approach. Limited applicability. The greedy algorithm is not applicable when the jobs have unit time. It may not work optimally or at all if the jobs have different time requirements. Lack of flexibility. The greedy algorithm does not consider future job assignment and may miss out on better long term profits again. Non optimality for general cases. While the greedy algorithm provides a an optimal solution for unit time jobs, it does not guarantee optimality when jobs duration vary on when there are additional constraints. Sensitivity to input order. The algorithm's output can vary depending on the order of the input jobs, which may result in different profits. Now, the next question is, derive the time complexity of the iterative and recursive version of the Fibonacci function to compare their efficiency in each case. The time complexity of the iterative version of the Fibonacci function is order of n, where n is the input number. This is because the iterative version uses a loop to calculate the Fibonacci series iteratively, and the loop executes n times to calculate the nth Fibonacci number. The time complexity of the recursive version of the Fibonacci function is exponential, especially order of 2 to the power n. This is because the recursive version make multiple recursive calls to calculate Fibonacci series, resulting in a branching tree of function calls, and the number of function call grows exponentially with the input number, leading to exponential time complexity. In terms of efficiency, the iterative version is more efficient than the recursive version for calculating Fibonacci number. The recursive version has exponential time complexity, which means it can become very slow for larger input number. On the other hand, the iterative version has linear time complexity and can handle large inputs more efficiently. Now, the next question is, explain chained matrix multiplication with a suitable example and discuss its practical implementation. Chain matrix multiplication refer to the process of multiplying multiple matrices together in a specific order. This is done by first multiplying two adjacent matrices, then multiplying the result with the next matrices, and so on until all matrices are multiplied. For example, let's consider three matrices: A with a dimension 2 cross 3, B with a dimension 3 cross 4, and C with a dimension 4 cross 2. To find the result of multiplying these matrices into B into C, we can compute A into B first, which will result in a matrices with a dimension 2 cross 4. Then we multiply this intermediate result by matrix C, resulting in a final matrix with dimension 2 cross 2. Chain matrix multiplication has several practical applications, particularly in fields such as computer graphics, optimization, and numeric simulations. Some examples include computer graphics. In 3D graphics, transformations such as scaling, rotation, and translation are represented using matrix. Chain matrix multiplication allow efficient computation of these transformations, enabling realistic rendering of complex scenes. Optimization. Chain matrix multiplication play a crucial role in optimization algorithms such as dynamic programming. Numerical simulations. Many scientific and engineering simulations involve solving system of linear equations representing as matrix equations. Chain matrix multiplication allow efficient computation of these equations, leading to faster and more accurate simulations. Overall, we can see that chain matrix multiplication is a fundamental operation with a widespread application in various domains that deals with large scale computations involving matrices. Its efficient implementation can significantly improve the performance and accuracy of many algorithms and simulations. Now let's move to the next question. The next question is, evaluate the time complexity of chain matrix multiplication and analyze how it affects the overall performance of an algorithm that uses this operation. The time complexity of chain matrix multiplication depends on specific order in which the matrices are multiplied. Let's assume we have n matrices to multiply. The optimal order for matrix multiplication is determined by the parenthesization of the matrices. The time complexity to multiply two matrices of dimension A cross B and B cross C is order of A into B into C. That is order of n square, n cube. For chain matrix multiplication, the overall time complexity is given by the product of the time complexity of all matrices multiplication involved. This can be computed using dynamic programming with a time complexity of order of n cube, where n is the number of matrices. The performance of an algorithm that heavily relies on chain matrix multiplication can be significantly affected by the time complexity. As the number of matrices increases, the time complexity grows rapidly. Therefore, the performance of the algorithm can uh, decrease quickly, resulting in longer execution times. It is crucial to consider the time complexity of chain matrix multiplication and optimize it when possible to maintain a satisfactory overall algorithm performance. Now let's move to the next question. Use a critical lens to describe traveling salesperson problem using dynamic programming and discuss its potential benefits and limitation involving optimization problem. The traveling salesman problem is a classical optimization problem that involves finding the shortest possible route for a salesperson to visit a set of cities and return to the starting point. Dynamic programming is a widely used technique to solve the traveling salesman person efficiently. Benefit of using dynamic programming for TSP includes: the first is optimal solution. Dynamic programming guarantees finding the optimal solution for small to medium sized instance of the TSP. The second one is time complexity improvement. By breaking down the problem into smaller subproblem and storing their solutions, dynamic programming reduces redundant calculations, resulting in a significant time complexity improvement. However, dynamic programming for the TSP also has some limitations. The first one is combinatorial explosion. The number of subproblems to solve grows exponentially with the number of cities, making dynamic programming impractical for large scale instances of the TSP. Memory requirements. Dynamic programming requires storing solution for all subproblems, which can lead to high memory usage for large problem sizes. Lack of flexibility. Dynamic programming assumes that the subproblems and their solution can be defined in a recursive manner, limiting its applicability to problems that can be decomposed in this way. In summary, while dynamic programming is an effective approach for solving the TSP and provides optimal solution, it may face scalability and memory limitation, making it less suitable for solving large-scale instance of the problem. Other optimization techniques such as approximation algorithm or heuristics are often used to tackle larger TSP instances. Now let's move to the next question. Write a non-deterministic search and sort algorithm. Non-deterministic search and sort algorithm, also known as probabilistic algorithms, uses randomness to improve their performance or efficiency. Here is an example of non-deterministic search and sort algorithm. The first we can see non-deterministic search algorithm. Start with an unsorted list of elements. The next step is randomly select an element from the list. The next step is check if the selected element matches the target element. If it does, return the index of the element. If it doesn't, repeat the step 2 and 3 until a match is found or all elements have been checked. Now we can see the algorithm for non-deterministic sort. Uh, Step 1 is start with an unsorted list of elements. Step 2, repeat the following step until the list is sorted. Randomly select two elements from the list. Compare the selected elements and swap their position if necessary. Step 3 is continue repeating step 2a and 2b until the list is sorted. The final step is it is important to note that the non-deterministic search and sort algorithm may not always produce the same result for the same input due to their random nature. They can be useful in certain scenarios, but deterministic algorithms are typically preferred for their predictability and producibility. Now, let's move to the next question. And the next question is, analyze and compare the class P, NP, NP hard, and NP complete problem and provide examples of each case. Discuss their significance in computer science and their potential real world application. Now, first we discuss what is P class problems. P is the complexity class that represents problem that can be solved in a polynomial time by a deterministic Turing machine. These problems have efficient algorithms that can find a solution within a reasonable amount of time as the input size grows. Example of P problems include sorting an array, finding the shortest path in a graph, and checking if a number is prime. Now, next we discuss what is NP problems. NP, non-deterministic polynomial, is it's a complexity class that represents problem for which a potential solution can be verified in a polynomial time. In other words, if someone claims to have a solution, uh, it can be checked efficiently. However, finding the solution itself will not be as efficient. The many real world problems fall into the NP class, such as the traveling salesman problem, the knapsack problem, and the Boolean satisfiability problem. Now, NP hard. NP hard, non-deterministic polynomial hard problems, at least as hard as the hardest problem in the NP. These problems may not necessarily be in NP, but they share a similar level of difficulty. Solving NP hard problem is the worst case requires exponential time. Example of NP hard problems include the traveling salesman problem, the vortex cover problem, and the bin packing problem. NP-hard problems have significant importance in the computer science as they serve as a benchmark for the difficulty of solving other problems. They are often used to design approximations. Now, let's discuss about NP-complete problem. NP-complete problems are the most challenging problem in NP. They are both in NP and NP-hard, meaning that they have the dual properties of being verifiable in a polynomial time or being at least as hard as any problem in NP. A solution for one NP complete problem can be efficiently transformed into a solution for any other NP complete problem. The most famous NP complete problem is the Boolean satisfiability problem, which asks whether a given Boolean formula can be satisfied. Other example of NP complete problems include the traveling salesman problem and the knapsack problem. Thank you for watching.